Look at your hands. I mean, right now, as you listen to this, just look at them. Because there are countless invisible versions of you splitting off into parallel realities at this exact second.
Right, which is just a wild thing to try and wrap your head around.
It really is. Like, in one reality, you pause this audio. In another, you keep listening. And in another, maybe you never even started.
Yeah.
And the truly staggering part isn't just that these alternate versions of you exist out there somewhere. It's that they're all equally real.
Exactly. They are governed by the exact same physical laws.
Right. And they're completely unaware of each other.
Yeah.
So welcome to the deep dive. Our mission today is to, well, basically strip away the comforting illusions of your everyday reality.
We're going right into the deep end today.
We really are. We are diving straight into the heart of the many worlds interpretation of quantum mechanics. And we're doing this guided by the incredibly profound framework laid out by theoretical physicist Sean Carroll in his book, Something Deeply Hidden.
Yeah, and we're asking you to basically leave your classical intuition at the door for this one.
Highly recommended, yes.
Right, because we aren't going to just, marvel at quantum weirdness as if it's some kind of incomprehensible magic trick.
No magic here.
The goal is to prize clarity over mystery. We really want to understand the profound elegance of a universe that constantly branches.
And we're going to push even further, right?
Yeah.
We're going to explore the mind-bending idea that space and time themselves, aren't fundamental at all.
Yeah, that they're merely illusions, things emerging from a deeper, invisible quantum reality.
It's just nuts.
Yeah.
So to understand how reality gets so fragile, I guess, we have to rewind to the moment the scientific consensus effectively gave up on trying to understand it.
Let's go to Brussels.
Yes, Brussels, 1927, the Solvay Conference.
A legendary gathering.
Oh, absolutely.
Yeah.
This is the gathering of the most brilliant minds of the 20th century. I'm talking Marie Curie, Max Planck, Werner Heisenberg.
And critically for our story today, Niels Bohr and Albert Einstein.
Exactly. By this point, the experimental evidence for quantum mechanics was undeniably real, right? They knew energy and light behaved in these discrete packets, or quanta.
Right. The math worked perfectly. No one was debating the math.
But the friction here, the real spark that ignited a century-long debate, was about what that math actually represented in the physical world.
It was basically a philosophical war zone. You had Bohr championing what would later become the Copenhagen interpretation.
And Bohr's stance was radically instrumentalist, wasn't it?
Oh, completely. He essentially argued that the mathematical wave function, the tool we use to calculate the probability of a quantum event, isn't a physical object at all.
It's just a recipe.
Exactly, just a recipe. You plug in the numbers, you get a probability, you make a measurement, and boom, you get a result.
But if you ask what the particle is doing between measurements,
or what it's doing when no one is looking.
Right, then Bohr says that's a fundamentally meaningless question.
Yeah, Bohr literally thought you weren't allowed to ask that.
Which, is the textbook recipe physics students have been fed for decades now.
The famous shut up and calculate mentality.
Yes, just use the tool, don't ask what reality is.
Yeah.
And Einstein, well, he found that completely unacceptable.
He was furious. He viewed it as a profound abdication of the duty of a physicist.
Because Einstein was a strict realist.
Exactly. His absolute line in the sand was that a physical theory must describe an objective reality, one that exists totally independently of human observation.
Right, the idea that a particle doesn't have a definitive state until some conscious observer or a measuring device interacts with it, that just seemed absurd to him.
He felt it reduced physics to a form of mysticism, honestly.
And he wasn't just annoyed in private, he actively campaigned against it.
Oh yeah, the EPR paper.
Yes, there is this fascinating saga from 1935. Einstein co-authored the EPR paper with Boris Podolsky and Nathan Rosen.
Such a dramatic story.
It really is. They designed this brilliant thought experiment intended to prove, once and for all, that quantum mechanics had to be incomplete.
That there just had to be some deeper hidden variables we couldn't see yet.
Right. But before the paper even went through formal academic channels, Podolsky leaked the findings to the press.
Einstein was so mad, he referred to it quite disparagingly as the secular press.
He did. The New York Times actually runs this massive headline declaring, "Scientist and two colleagues find it is not complete, even though correct."
And the betrayal Einstein felt was just absolute.
He was fiercely protective of the integrity of the scientific process. He actually cut Podolsky off completely.
Never spoke to him again.
Never spoke to him again. Which really shows you the sheer emotional gravity of this debate. Einstein wasn't just debating equations here.
Oh, he was fighting to defend the very definition of reality itself.
Exactly. And to grasp why Einstein felt his back was against the wall, we have to look closely at what the Copenhagen interpretation was actually demanding people accept.
Right, specifically Werner Heisenberg's uncertainty principle and the concept of complementarity.
Let's drill into that for a second, because the pop culture understanding of the uncertainty principle is, well, it's fundamentally flawed.
Oh, completely.
People usually think of it as a clumsiness problem, like, a particle is a tiny billiard ball, but our microscopes are too brute force to measure its location without bumping it.
Right, like we bump it and change its momentum.
Yeah, so we can't know both at the same time. But that's not what the math is saying at all, is it?
Not even slightly. It's not about the limits of human technology or clumsy microscopes.
Wait, really? So it's not a measurement error thing?
No, it is a fundamental statement about the ontological state of the universe. Basically, what cannot be known does not exist.
Whoa. Okay.
An electron before a measurement is not a tiny sphere hiding in a specific location that we just happen to be ignorant of.
So what is it then?
The electron is the wave function. It exists as a superposition of all possible locations and momenta.
So it literally does not possess a precise position.
Not until the exact moment it is forced into one through observation.
Okay, so if I throw a baseball, it has a continuous, measurable trajectory through the air.
Right, classical physics.
But if I fire an electron, it doesn't have a trajectory. It's just a smeared out cloud of probability. Maybe.
Exactly. And the Copenhagen crowd says that when you finally measure it, that massive, smeared-out wave function instantaneously collapses into a single localized point.
Instantly collapsing.
That is the Copenhagen mechanism, yeah. The wave function collapse. And this is exactly what troubled Einstein.
I can see why.
Because it gets infinitely more problematic when you introduce the concept of quantum entanglement.
Right, because if a single particle is a smeared out cloud of probability, what happens when two of these particles interact and then move apart?
This is where we hit Einstein's famous spooky action at a distance.
Let's walk through the mechanics of entanglement, because it's really the cornerstone of everything that comes later in the deep dive.
Sure. So when two quantum systems interact, their wave functions don't just briefly touch and then go their separate ways.
They don't just bounce off each other.
No, they merge. They become a single mathematically unified wave function that exists in what physicists call configuration space.
Okay.
And even if you send one particle off to the other side of the Milky Way, they are still described by that one single wave equation.
Okay, so if I have two entangled particles, and they are in a superposition where they must spin in opposite directions.
Right. One clockwise, one counterclockwise.
But neither particle has, decided which way it's spinning yet.
Yeah.
They are both in this cloud of maybe clockwise, maybe counterclockwise.
Yes.
If I measure my particle here on Earth, and it suddenly collapses into a clockwise spin,
then the particle on the other side of the galaxy instantaneously, with literally zero time delay, collapses into a counterclockwise spin.
But wait, that completely shatters the cosmic speed limit. Information can't travel faster than light.
It can't.
So how does the second particle know to collapse instantly? How does a purely mathematical link manifest physically across that vast distance?
Well, according to the Copenhagen interpretation, you shouldn't ask that question.
Oh, come on. Just don't ask.
Seriously, you just accept that the wave function collapses everywhere at once. But you can see why Einstein called it spoopy.
Yeah, it blatantly violates the principle of locality.
Exactly, the idea that things can only be influenced by their immediate surroundings.
Right. Copenhagen essentially demands we accept that a miracle occurs right at the moment of measurement.
A miracle that operates instantaneously across the entire universe.
And we are strictly forbidden from asking how it happens. That feels like such an intellectual cop-out.
A lot of people felt that way.
You have this beautiful deterministic equation, the Schrödinger equation, that perfectly describes how the wave function evolves over time.
Beautiful math.
Beautiful math. And then arbitrary observers enter the picture. The beautiful math is just thrown out the window, and reality violently snaps into a single state for literally no mechanical reason.
And that intense dissatisfaction is exactly what set the stage for a young Princeton graduate student named Hugh Everett III in the 1950s.
Enter Hugh Everett.
Everett looked at this ad hoc, messy collapse postulate and asked a remarkably simple yet completely radical question.
Which was?
What if we just stop making up rules? What if the Schrödinger equation is the only rule?
And that Right there is the birth of the many worlds interpretation.
Yes. Sean Carroll actually refers to it as austere quantum mechanics.
Austere because it strips away all the excess baggage.
Exactly. There are no magical observers in this framework. There is no instantaneous wave function collapse.
So what is there?
There is only the wave function, evolving smoothly and deterministically forever.
Everett's brilliance was in realizing that the observer isn't some magical entity standing outside the universe, right?
Right. The observer, the scientist, the measuring device, you and me, we are all made of atoms.
We're all quantum systems, too.
Precisely. Therefore, we must also obey the Schrödinger equation. We don't magically collapse it.
Let's talk about Everett for a second, because the resistance to his idea was just monumental.
Oh, it was a rough road for him.
He was doing his PhD under John Wheeler, who was a total titan of physics, but also deeply loyal to Niels Bohr and the Copenhagen establishment.
Wheeler revered Bohr.
So Everett's initial draft was basically a frontal assault on the Copenhagen interpretation.
And Wheeler made him heavily sanitize it, right?
Yeah, to avoid offending Bohr. But Everett was pretty sly. When the paper was in the final proofing stage, he literally sneaked the word splitting into a footnote.
That's hilarious. Into a footnote.
Yes. He smuggled the entire concept of a branching multiverse into the academic record when his advisor wasn't looking.
It was a subtle rebellion, but a completely necessary one. Because splitting is exactly what the math demands if you refuse to add the collapse postulate.
Right. If the wave function never collapses, we have to explain why we only ever experience one single outcome.
Let's go back to our entangled particles for a second to illustrate this.
Okay, let's do it.
I have a particle in a superposition of spinning clockwise and counterclockwise. I measure it. I only ever see it doing one or the other.
Right. You never see a blurry superposition particle with your bare eyes.
So if the wave function didn't collapse and magically eliminate the other possibility, where did it go?
It didn't go anywhere. You split.
Or, more accurately, the universe branched.
The universe branch.
Yes. And to understand this, we need to trace the exact physical mechanism of what happens during a measurement. We really need to talk about decoherence.
Yes, I want to demand the mechanism here.
Here.
Because it sounds like sci-fi. How does a single microscopic particle's uncertainty infect the entire universe and cause it to branch?
It's a cascade of entanglement. It happens because the particle doesn't exist in a vacuum. It exists in a messy macroscopic environment.
Okay, paint the picture for me.
Let's say your particle is in that superposition of clockwise and counterclockwise. Now, a single photon of ambient light in the room bounces off it.
Just one photon.
Just one. The moment it bounces, the photon's wave function merges with the particle's wave function.
So they entangle.
Exactly. The photon is now in a superposition of having bounced off a clockwise particle and having bounced off a counterclockwise particle.
What now?
But it doesn't stop there. That photon flies into the lens of your measuring device.
Okay.
Now the measuring device is entangled. The dial on the machine is literally in a superposition of pointing to clockwise and pointing to counterclockwise.
And then I look at the dial. The photons from the dial hit my retina, trigger my optic nerve, and enter my brain.
And now you are entangled.
Me. I am in a superposition.
Yes. There is now a wave function for you seeing the dial point to clockwise and a separate wave function for you seeing the dial point to counterclockwise.
But I don't feel like I'm in two states at once. I never feel blurry.
Because the moment you become entangled, you interact with billions of other particles in the environment. Air molecules, thermal radiation,
The rest of the room.
the rest of the universe. This interaction happens almost instantaneously, and it causes the two states to mathematically separate into orthogonal, non-interacting branches.
And that is decoherence.
That is decoherence. The superposition has leaked out of the isolated quantum system and swallowed you.
And the universe has split into two parallel realities.
Exactly. In one branch, a fully conscious version of you sees a clockwise spin. In the other, a fully conscious, completely identical version of you sees a counterclockwise spin.
And because these branches are orthogonal, meaning they are mathematically perpendicular in configuration space, they can never interact again.
Never.
I can never communicate with the me who saw the other result.
Right. So to your localized perspective, it looks exactly like the wave function collapsed.
It looks like the other possibility just vanished.
But in reality, it's playing out in a universe right next door.
That is just the
Yeah.
austere elegance of many worlds is undeniable. It solves the measurement problem not by inventing new physics,
Right.
but by taking the physics we already have entirely, literally.
It's beautiful in its simplicity.
Okay, but this introduces a massive, massive headache when it comes to probability.
Ah, yes. The probability problem.
Because if I flip a quantum coin, the math of the Copenhagen interpretation, the Born rule, gives me a probability. Say, a 50% chance it lands heads, a 50% chance it lands tails.
Right.
Probability implies that one thing happens and the other thing doesn't. But in the many worlds framework, if I flip the quantum coin, the universe splits, and both outcomes happen with 100% certainty.
Every single time. Both happen.
So if everything happens everywhere, all the time, what does a 50% chance even mean? Or worse, what if the math says there's an 80% chance of heads and a 20% chance of tails?
Yeah, how can one outcome be more probable than another if both are guaranteed to exist?
Exactly. If both versions of me are guaranteed to exist, what does the 80% actually represent?
This was the major stumbling block for many worlds for decades. How do you recover classical probability in a perfectly deterministic, all-inclusive multiverse?
And Sean Carroll leans heavily on the concept of self-locating uncertainty to solve this, right? Drawing on the work of philosopher David Albert.
He does, the fatness measure.
Let's dive into this fatness measure, because it is brilliant, but it really twists your brain.
It does. To understand the fatness measure, you have to place yourself in the exact moment after the split has occurred, but before you have looked at the result.
Okay, so the particle has interacted with the environment.
Right. Decoherence has happened incredibly fast, faster than your brain can even process. There are now two branches and two versions of you.
So I'm sitting there, my eyes are closed, but the universe is already duplicated.
Precisely. At this specific moment, you have a gap in your knowledge.
What don't I know?
You know the universe split, but you do not know which branch you are currently occupying.
Because my eyes are closed.
Yes. This is self-locating uncertainty. It's an epistemic probability, meaning it's a probability based on your own ignorance of your location in the multiverse.
It's like waking up in a hotel room with amnesia. You know you are in a hotel, but you don't know which city you are in.
That is a perfect analogy. Now, how do you place a bet on which branch you are on? This is where Albert's fatness measure comes in. When the Schrödinger equation evolves, it doesn't just create branches. It assigns a mathematical weight or amplitude to each branch.
Okay, so if the math dictates an 80-20 split, it's not saying there's an 80% chance of an event happening.
No.
It's saying the branch where that event happens is physically thicker. It carries 80% of the weight of the universal wave function.
Yes. The universe doesn't split into two equal halves. It splits into a thick branch and a thin branch.
Fascinating.
And if you are a rational agent who has just awoken in this newly branched multiverse and you know you are randomly located on one of these branches, you should mathematically assign a higher credence to finding yourself on the thicker branch.
Because there's quite literally more reality there.
Effectively, yes. Your subjective experience of anticipating an outcome perfectly mimics classical probability, even though the objective evolution of the universe is completely deterministic.
That is so wild. I experience uncertainty because I can't feel the weight of the whole multiverse. I could only experience the localized reality of the branch I just happen to be on.
Exactly. You are confined to your branch.
But wait, this brings up another huge issue. If I have an endless number of doppelgangers out there making every possible choice, experiencing every possible outcome, doesn't that render my choices completely meaningless?
The existential dread question.
Yeah, this is the dread that Carroll addresses. Why should I even try to be a good person or strive for anything if a bad me or a lazy me is out there robbing banks and failing anyway? Doesn't many worlds just destroy free will and human meaning?
It's a profound philosophical trap, but Carroll argues it's based on a fundamental misunderstanding of identity.
How so?
He approaches this through the lens of compatibilism. The mistake we make is trying to adopt a God's eye perspective of ourselves.
What does that mean?
We try to imagine a unified self that somehow hovers above the multiverse, experiencing all branches simultaneously.
But I'm not the universal wave function. I'm just a guy sitting in a chair.
Exactly. You are a localized, highly specific pattern of information within a single branch. The you on this branch only has access to the history, the memories, and the consequences of this specific branch.
So the choices you make here are entirely yours.
Yes.
So if I decide to go to the gym instead of sitting on the couch, the effort I put in, the sweat, the health benefits, those are real and localized to my branch.
Completely real to you.
The fact that another version of me on a different branch chose the couch doesn't invalidate my reality.
It has zero operational effect on you. You cannot interact with CouchMe, you don't share their memories, and you don't share their clogged arteries.
That's a relief.
Therefore, you must make moral, ethical, and practical decisions based entirely on the reality you inhabit. Carroll asserts that living in a quantum universe changes absolutely nothing about how we should live our daily lives.
The multiverse is vast, but your moral horizon is local.
Beautifully put, yes.
I see how that rescues agency. But let's play devil's advocate for a moment here.
Do it.
Because Sean Carroll doesn't just preach many worlds in the book, he systematically evaluates the alternatives. And a lot of brilliant physicists absolutely loathe many worlds.
Oh, they despise it.
They hate the ontological extravagance of it, postulating an infinite number of unobservable parallel universes just to avoid adding a collapse rule to the math feels, to many, like a massive violation of Occam's razor.
It does feel heavy.
So what are the other options on the table, and why does Carroll think they fail?
Well, the resistance usually spawns two main alternative theories: Bohmian mechanics and objective collapse models. Both attempts aim to keep reality singular, just one universe.
Let's look at Bohmian mechanics first. This is often called pilot wave theory, right?
Right.
This is where we bring hidden variables back into the mix, trying to fulfill Einstein's dream.
Yes. Bohmian mechanics proposes that particles actually do have precise localized positions at all times.
So they aren't smeared out clouds of probability.
No, they are real, point-like particles. The catch is that their motion is deterministic, but it's guided by a universal, invisible entity called the pilot wave.
So the wave function isn't the particle. The wave function pushes the particle.
Precisely. Well, I should say that's the core distinction. The uncertainty we observe in the lab isn't because the particle lacks a location.
It's because we, the observers, are hopelessly ignorant of the intricate universal details of the pilot wave guiding it.
Exactly. We just don't know the hidden variables.
And what's Carroll's objection to that? I mean, it gives us a single universe. It solves the measurement problem. Einstein would be happy.
Carroll argues it is deeply unaesthetic and mathematically clunky.
Clunky how?
To make Bohmian mechanics work, you have to keep the entire Schrödinger wave function, which, as we discussed, naturally branches.
Right.
But then you have to bolt on all this additional complex mathematical machinery just to define these invisible particles surfing on top of it.
So you're adding extra math.
You are adding incredibly heavy mathematical scaffolding that serves literally no other purpose than to hide the other branches of the multiverse from our view.
It's like building a massive, intricate stage play, but forcing the audience to look only at one single actor with a spotlight while completely ignoring the rest of the cast.
That's a great way to think about it. It violates Occam's razor in a different way. Many worlds multiplies entities, universes,
Right.
but Bohmian mechanics multiplies rules. And Carroll, and honestly many theoretical physicists, prefer keeping the rules as simple as possible.
Okay, so what about the other route? Objective collapse theories. The most famous one mentioned in the source is GRW theory, named after Ghirardi, Rimini, and Weber.
Right, GRW takes a completely different approach. It accepts that the wave function is real and that it describes a superposition,
Okay.
but it proposes that wave functions do physically collapse. And it has absolutely nothing to do with conscious observers or measurement devices.
So how does it collapse then?
Spontaneously. GOW theory suggests that every fundamental particle in the universe has a tiny, built-in, random chance of collapsing into a definite position all by itself.
Just spontaneously, like a timer.
Sort of. For a single, isolated electron, this spontaneous collapse might happen once every 100 million years.
Which means if I'm studying a single electron in a lab, it behaves perfectly like a quantum wave. It won't collapse while I'm watching it.
Right. But a measuring device, or a human being, isn't a single electron.
No, a macroscopic object is made of a trillion atoms.
Exactly. So if every single one of those atoms has a tiny chance of collapsing every second, then statistically, in a massive object, something is collapsing constantly.
Oh, I see.
And because all these atoms are entangled, the collapse of one atom triggers the collapse of the entire macroscopic system almost instantly.
That is actually a very clever workaround. It explains why the microscopic world is fuzzy and quantum, but the macroscopic world we live in appears solid and classical.
It is clever.
So why does Carroll reject this? It sounds pretty good.
Because to make GRW work, you have to fundamentally alter the Schrödinger equation. You have to introduce nonlinear mathematics to force the collapse.
And I'm guessing that's bad.
Very bad. When you make quantum mechanics nonlinear, you open up a Pandora's box of paradoxes. Carroll points to a brilliant thought experiment by physicist Joe Polchinski to illustrate this, the Everett phone.
Ah, the Everett phone. This is one of the wildest concepts in the source material. How does nonlinear math allow me to make a trans-dimensional phone call?
Well, in the pure linear math of many worlds, once decoherence happens, the branches of the wave function are perfectly orthogonal. They are mathematically perpendicular.
Meaning they can never interact again.
Right. They can never, ever interact or interfere with each other again. But if you tweak the equations to force a collapse, if you introduce nonlinearity, you break that perfect orthogonality.
And create a loophole.
A mathematical loophole, yes. Polchinski showed that in certain nonlinear variants of quantum mechanics, a microscopic degree of communication could theoretically leak between parallel branches before they completely decouple.
Wait, meaning I could theoretically build a device, the Everett phone, that sends a signal from my branch to a parallel branch.
That's the theory.
I could call the version of me who is about to make a bad investment and say, hey, don't buy that stock.
Which immediately shatters causality.
Oh, right.
You alter the past of another universe, creating massive logical paradoxes.
So the math just breaks down into chaos.
Exactly. Carroll's point is that the Schrödinger equation is perfectly linear and that linearity protects the universe from causal chaos.
Every attempt to modify the math to avoid many worlds ends up creating logical nightmares. Nightmares that are far worse than just accepting the existence of parallel universes.
Exactly. You either accept the branching or you accept time travel paradoxes and broken physics.
Okay, so if we take Carroll's premise to its logical conclusion,
Yeah.
we don't add hidden variables, we don't add spontaneous collapse.
Right.
We accept the austere, terrifyingly simple reality that the universe is just a single, endlessly branching wave function. If that is true, we have to tackle the final and undoubtedly most difficult part of this deep dive, space-time itself.
Oh, yes. This is where we leave the realm of near quantum weirdness and enter the absolute frontier of modern physics.
Because I'm looking around me right now, I perceive distance. I perceive 3 dimensions of space. I see a microphone in front of me, a wall behind it.
Sure.
If the fundamental bedrock of reality is just a mathematical wave function existing in some abstract multidimensional configuration space, where does the physical room I am sitting in actually come from?
The radical thesis of the latter third of the book is that space is not fundamental. Space, as we experience it, is an illusion.
That is a staggering claim.
Yeah.
Let's really unpack that slowly. What do you mean space isn't fundamental? Newton told us space was the absolute rigid stage on which the universe plays out.
Right, the absolute stage.
And then Einstein showed that the stage could warp and bend under gravity, but it's still the stage.
Carroll is arguing that the stage itself doesn't exist at the deepest level of reality.
Then what is it?
To understand this, we need to think about emergent properties. The book uses the analogy of temperature, and we really need to drill down into why that analogy is so powerful here.
Let's do that. Think of a cup of coffee.
Yeah.
I can measure its temperature. It's hot.
Yeah.
But if I take a microscopic pair of tweezers and pull out a single water molecule and ask, what is the temperature of this molecule? The question makes no sense.
Because a single molecule doesn't have a temperature.
Exactly.
Temperature is not a fundamental property of matter. It is a statistical description. It's what we call the average kinetic energy, the collective jiggling and bouncing of billions of molecules interacting together.
So temperature emerges from the complex interactions of fundamental parts.
Precisely. And Carroll, synthesizing ideas from quantum field theory and quantum gravity, is arguing that space itself, distance, geometry, the whole three-dimensional grid we live in, is exactly like temperature.
Wait, really? Space is like temperature?
Yes. A single, isolated quantum degree of freedom doesn't have a location. It doesn't have coordinates. Space is what emerges when you zoom out and look at the incredibly complex network of quantum entanglement between billions of degrees of freedom.
I really want to demand the mechanism here. How does a mathematical link between particles entanglement create the physical sensation of the space between my hands?
To get there, we have to flip our classical understanding of locality upside down.
Locality being the rule that things only interact with things directly next to them.
Right.
I have to touch my coffee cup to move it. The sun's gravity pulls the Earth because the gravitational field transmits that force continuously across the intervening space.
Yes. In classical physics, we say things interact strongly because they are close together in space.
That makes sense.
But in emergent spacetime, the causality runs in the opposite direction. We define close together in space by observing which parts of the wave function interact strongly.
Wait, so distance is just a measurement of entanglement?
That is the core idea. Imagine the universal wave function as a massive abstract network of nodes.
Okay, visualizing a network.
Some nodes are highly entangled with each other. They share a lot of mutual information. Other nodes are barely entangled at all.
Right.
Carroll suggests that what we perceive as distance is simply a measure of how entangled two parts of the quantum state are.
That is incredible.
High entanglement translates to close together. Low entanglement translates to far apart. The geometry of space is literally woven out of quantum entanglement.
So if I walk across the room, I'm not traversing an empty void. I'm navigating a gradient of entanglement.
Exactly.
My physical coordinates are just a macroscopic translation of how my wave function is mathematically interacting with the wave functions of the floor, the air, and the walls.
You are surfing a web of mutual information. And this isn't just theoretical poetry, by the way. This approach is currently one of the most promising avenues for solving the biggest crisis in modern physics.
Which is the unification of quantum mechanics and general relativity.
Exactly.
Which brings us to the ultimate crucible for these theories. Chapter 14. Black holes.
The monsters of the universe.
Why do black holes force us to rethink space so drastically?
Because black holes are where Einstein's general relativity and quantum mechanics collide head-on, and historically they produce mathematical nonsense when you try to combine them.
Right, because a black hole is a region of space where gravity is so intense, space bends in on itself. Classically, nothing escapes.
But then Stephen Hawking applied quantum mechanics to the edge of the black hole, the event horizon.
Right. And Hawking discovered that due to quantum fluctuations, virtual particles popping in and out of existence near the horizon, black holes must emit radiation.
They glow, and if they glow, they have a temperature.
And according to the laws of thermodynamics, if something has a temperature, it must have entropy.
Entropy being a measure of hidden information, the number of microscopic states that make up a macroscopic object.
Exactly. So a black hole contains a massive amount of quantum information. But the mind-bending crisis arose when physicists calculated how much entropy a black hole actually has.
Right, because if I have a box of gas, the entropy, the amount of information, is proportional to the volume of the box.
Makes sense. A bigger 3D box holds more information.
But Jacob Bekenstein and Stephen Hawking proved that the entropy of a black hole is not proportional to the 3D volume inside it.
What is it proportional to?
It is strictly proportional to the 2D surface area of its event horizon.
Let me make sure I'm getting this. All the information of everything that ever fell into that three-dimensional black hole, the stars, the planets, the dust, all of that 3D reality is mathematically encoded on the two-dimensional boundary surrounding it.
Yes.
That is just hard to process.
It is. This discovery gave birth to the holographic principle, famously championed by Juan Maldacena. It is the realization that our three-dimensional universe might just be a holographic projection of information encoded on a lower dimensional boundary.
How does that connect with what we were just saying about space being an illusion?
Think about what happens to locality at the surface of a black hole. If all the information of the inside is entirely accessible and encoded on the outside boundary,
then the strict geometric distinction between inside and outside ceases to exist at the fundamental level.
Exactly. When gravity becomes overwhelmingly strong, the geometry of space literally tears at the seams.
The hologram glitches.
The hologram glitches, revealing the pure, unadulterated quantum wave function underneath.
Wow.
Black holes are the glowing exit signs pointing to the limits of spacetime. They tell us that if we want to understand quantum gravity, we cannot just try to quantize space, as physicists have tried to do for decades.
We have to figure out how space emerges from the wave function in the first place.
Precisely.
Man, this has been a monumental journey. Let's try to synthesize everything we've mapped out today.
It's a lot of ground.
We began by looking back at the 1920s, exploring the deep philosophical crisis triggered by the Copenhagen interpretation. We saw how Bohr urged us to ignore the underlying reality of the quantum world, and how fiercely Einstein fought for an objective universe.
Famously railing against the spooky action at a distance caused by quantum entanglement.
Right. We then shifted to the 1950s and Hugh Everett's courageous formulation. We discovered that by refusing to add arbitrary rules like wave function collapse, we are left with a universe that constantly, mechanically branches via decoherence.
Branching endlessly.
We learned that the probabilities we observe are not random cosmic rolls of the dice, but rather our own self-locating uncertainty, the fatness measure, as we navigate a deterministic splitting multiverse.
And importantly, we saw how our choices and our morality remain entirely valid within our localized branch.
Exactly. We analyzed the alternatives, Bohmian hidden variables and GRW objective collapse, and saw how trying to save a single universe model forces physicists to introduce clunky math and causal paradoxes like the Everett phone.
Which nobody wants.
And finally, we arrived at the profound bleeding edge of physics. We dismantled the concept of space itself, realizing that the distances and geometry we perceive are merely emergent properties like temperature born from a vast underlying web of quantum entanglement.
A reality laid bare by the holographic nature of black holes.
It's just incredible.
It is a profound and, frankly, humbling shift in perspective. If I can offer you one overarching takeaway from Carroll's work, it is a plea for intellectual courage.
Intellectual courage, I like that.
The history of physics is a history of discarding our intuitive safety blankets. We had to accept that the Earth isn't the center of the universe. We had to accept that time is relative.
And now we're being asked to accept that the universe is not a collection of solid objects acting on an empty stage.
Right. It's a majestic, endlessly branching wave function. Knowledge demands that we follow the math, no matter how weird the destination.
Well said. And as we end this deep dive, I want to leave you with one final, deeply visceral thought, drawn from the very end of the source material. We've spent a lot of time talking about matter in space today. But think about the vacuum.
The absolute nothingness.
Exactly. Think about absolute nothingness. According to quantum field theory, the empty space sitting between you and your speakers right now isn't empty.
Far from it.
Because of the very uncertainty and entanglement we've been discussing, the vacuum of space is furiously boiling. It is bubbling and frothing with virtual particles continuously popping into existence and annihilating each other.
A boiling sea of potential.
So next time you look across an empty room and you feel the comfort of that quiet, three-dimensional void, ask yourself, what invisible, entangled realities are breathing, vibrating, and perhaps even violently splitting into countless parallel worlds in the nothingness right in front of your eyes?